We continue with the mathematical foundations of stochastic processes, as we've been looking at a review of some probability concepts, because probability is central to the idea of stochastic processes. In this video, we look at joint distributions. In probability theory, we often study more than one random variable at the same time. Examples, you may be considering height and weight together. You may be looking at temperature and electricity demand. You may be looking at rainfall and crop yield. You may be looking at study time and exam score. And to describe probabilities involving two random variables together, we use a joint distribution. So if you let x and y be two random variables, the distribution describing both variables simultaneously is called the joint distribution. So, we look at joint distribution or the joint probability mass function rather for a discrete case. Of course, before now we already learned that we use PMF, that's probability mass function for discrete variables, and we use probability density function for continuous function for continuous case variables. All right. So if x and y are discrete random variables, their joint distribution is defined by the joint probability mass function PMF. Definition would be P of P x comma y of xy is equal to probability that x takes a value x and big Y takes a value small y. This represents the probability that x is equal to x and y is equal to y at the same time. And that is the essence of it being a joint probability mass function. So to learn about some properties of probability mass function, right? First of all, of course, just like probabilities in general, probability functions in general, there's non-negativity. That is, the function p of x comma y is always greater than or equal to 0. And of course, total probability equals 1. That is, if we sum over x and sum over y, the function p of x comma y, you always get 1. And that is why probabilities range from 0 to 1. So the least probability you would ever get will be 0, and the highest you would ever get will be 1. So if you get a negative probability, you know something is wrong somewhere. And if you get any probability bigger than 1, you know there's a problem for sure. So you can get anything from 0 to 1. So, example, if you are, let's imagine the probability mass function for two dice. So let x be equal to the result of die one. You know, a die has six faces, right? One, two, three, with one, two, three, four, five, six on each face, and y is the result of die two, right? So each die has values one, two, three, four, five, six. So because the dice are fair, so if you have a fair die, so that where you actually have a proper die, the normal die, not tampered with. So probability that x is equal to x and y is equal to y simultaneously is 1 over 36 for all combinations of x and y. So imagine the probability that x will be anything from 1 to 6 and anything from for y also will be anything from 1 to 6 will be 1 over 36 because that will probability that x is if it's imagine the probability that x is equal to 1 and probability that y is equal to 1, you know, that will be like 1 over 36 times 1 over 36. Yeah, that's 1 over 36 like that for every combination. Mm, okay, so the example here, probability that x is equal to 3 and y is equal to 5 is 1 over 36. So if we simulate that, right, you get if you run this now, see the can you get 0.02856. All right. So what do we do here? Imagine you are doing 10,000 simulations. So for die one now, you do it 9 times. I mean, and that's 100,000 times. So and you have values from 1 to 7. So we have 1 to 7 here because for Python it starts from 1, but it stops a step short of 7. So we have 1 to 6 in short. So if you do that simultaneously, like the thing has to be joint. So you have 0.02 0.02722. Okay, because it's random, right? So you keep having values very close to 0.277. So I actually printed 1 over 36 so that you can see that whatever you have here so will converge towards 0.277 as you keep trying and trying. So it just keeps go hovering around 0.27 like that. So we that takes us to look at joint probability density function for the continuous case. If x and y are continuous random variables, we use a joint probability density function PDF f sub x comma y into xy. This function describes how probability density is distributed across pairs of values. Again, properties of a joint probability density function. Non-negativity is the first, where f of x comma y is always greater than or equal to 0. And the total probability, if you do the double integral across both x and y, that is integral f of x comma y dx dy, would always be 1. Okay, so and that speaks to the idea of probability over a region. So for continuous variables, probabilities are computed using integrals. Example, you want to calculate the probability that x lies between a and b and y lies between c and d. So in that case, that will be equal to integral from a to b, integral from c to d of f of xy dy dx. So we have an example here now. So suppose that f of x comma y is equal to 2. That's the function itself for x lying between 0 and 1 and y lying between 0 and x. So, and 0 otherwise. So to verify this is a valid PDF, we check that integral from 0 to 1 and integral from 0 to x of 2 dy dx. So we need to verify it. So the first thing we need to do is to integrate with respect to y. So if you integrate with respect to y, right, you get, okay, I guess I need to do this actually so that it will be clear enough. So integral from, so we have f of x comma y to be 2 f of x comma y is equal to 2, and we have x lying between 0 and 1, and y is lying between 0 and x, I think. Yeah, y is lying between 0 and x. I think that's all we have there. Exactly that. Okay, so we can move on with this. So we now want to verify that this is actually a correct probability. I know the test is by the time you do the double integral, you must get 1. If you don't get 1, then it's not a proper probability density function. So 0, but that's joint probability density function. So you have 0 to 1 now. So I think it's better to, so one way to not get confused is you can say x is equal to 0 to 1, integral y is equal to 0 to x. So you know which one goes for which at any point in time. Or if you write the, okay, yeah, that's I'll just go straight. So I have 2 now, which is f of x comma y. Okay, this is what I've been I didn't want to do because of laziness. Okay, I wanted to do this. So integral x is equal to a to b, integral y is equal to c to d of f of x comma y dx dy is equal to 1. Usually that's what it should be for a joint probability density function. So now with that formula, we can go ahead and say this is integral x equals 0 to 1, integral y equals 0 to x of 2 dx dy dx, if you like. Any, you can start with anyone you like. So if you do this and we get 1, then we know it is proper. So the first thing we want to do is uh so okay, if you like, you want to arrange it this way. So you have integral from y equals 0 to x, and inside you have integral from x equals 0 to, okay, yeah, it's now, because we want to integrate y first, right? I want to arrange it in such a way. So you have integral from x equals 0 to 1. Then inside you have integral from y is equal to 0 to x for 2 dy. And all of this now dx. Yeah, that's a nice way to arrange it because we are dealing with y first. So now we have integral from x equals 0 to 1. You integrate 2 with respect to y, you get 2y, but of course you have y equals 0 to x. Of course, you have dx here. Then we go on with this now. So you have integral from x equals 0 to 1. So you put the values of y now. So you have 2 into x, because y is equal to x at the top, minus 2 into 0 because y is 0 down here, and all of that into dx. So that means you have integral from x equals 0 to 1, uh, 2x minus this is okay. Let me just go step by step. 2x minus 0 dx. And then you have integral from x equals 0 to 1, 2x dx, right? So now you integrate x. So you can bring out the 2 integral. Well, now I don't have to worry about the x again because we are only left with x. So in that case, I can just say 2 integral from 0 to 1 of x dx. 2 is out already because it's constant. So we have 2 into integrate x, you get x squared all over 2 from 0 to 1. Okay. So I always like to bring out the constant so that I can isolate the variable so we can deal with that decisively. So you have 2. If you bring out the half, you have 1 over 2 into x squared from 0 to 1. So this cancels this. So we just have x squared from 0 to 1. So lastly, so at 1, we have 1 squared minus at 0, we have 0 squared. And that is simply 1 minus 0, and that is 1. So that actually passes. So this is now integral from x equals 0 to 1, integral from y equals 0 to x of 2 dx dy. So that actually passes for a proper joint probability density function based on the second property. Okay, so that's how you go step by step with the integration. Therefore, it is a valid joint PDF like we've discovered. And that takes us to the concept of marginal distributions. Sometimes we want the distribution of a single variable only. So even in a joint distribution, you now want uh, the distribution of a single variable out of that joint distribution. So these are called marginal distributions. So you have marginal distribution for the discrete case. So marginal PMF of x now, that's marginal probability mass function, is P sub x of x equals summation. So you now sum over y, sum P of x comma y over y, and the marginal PMF of y is sum. So you have P sub y of y equals summation over x. So you sum P of x comma y over x now. So it means that if you do this over y, you are left with x. If you do this over x, you are left with y, because and that's how it goes. So imagine this example. You have x is 1 to here and y is 1 to here. And 1 is gives 0.2. The probability 1 x is 1, y is 1 is 0.2. Probability x is 1 and y is 2 is 0.3. Probability x is 2 and y is 1 is 0.1. Probability x is 2 and y is 2 is 0.4. So marginal distribution of x now will be probability that, so it is distribution of x, right? So probability that x is 1 in this case now will be you sum it over y. So that'll be 0.2 plus 0.2, you get 0.5. The probability that x is equal to 2, you have 0.1 plus 0.4, that'll be 0.5. So that's what you have in that case. Then if you're talking about marginal distribution of y, so for for the marginal distribution of x, is summed across the rows. But for marginal distribution of y now, you sum down the columns, right? So probability that y is 1 now, y is 1, that's you have 0.2 plus 0.1, that's 0.3. And of course, you see that the addition of everything, so it's 0.5, 0.5 summed up to 1, just like this one now. Probability that y is equal to 2, that's 0.3 plus 0.4, which is 0.7. So, and that is the idea of so this is the joint probability table now, and from that we can extract our marginal distribution. So we can also simulate with Python, and this is the setup right here, and you get for x now you have 0.5, 0.5, 0.3, 0.7, like that, to establish what we got right there. So talking about conditional probability now. Conditional probability answers the question, what is the probability of one variable given that another variable is known? So if you know this variable, what is the probability that we can get this other one? So conditional probability formula is this. For discrete variables, probability that x is equal to x, given that y is equal to y, is equal to probability that x is x, y is y, all over probability that y is y. And for x, now probability that y is equal to y, given that x is equal to x, is equal to probability that x is x and y is y, all over probability that x is equal to x. So the the variable that is already known is always the numerator, because you read it like probability that y is equal to y given that x is already x, as you know. So that's given that part is what we have as a numerator. So an example of that is what we have here now. From the joint table, see that joint table up there? Yeah, this table. From that joint table, so we need probability that x is equal to 1 and y is equal to 2. So if we probability that x is 1, y is 2, right? That is probability that x is equal to 1, you know, x is 1 and y is 2. That's 0.3 right here. And that's why we have that 0.3. And then you don't have, so if you need probability that x is equal to 1, given that y is equal to 2, so you need probability that, what is the probability that y is equal to 2? So probability that y is equal to 2, all right, is that would now be marginal, right? Probability that y is 2, you have to sum across down the column. That's 0.3 plus 0.4. So because y can be 2 in these two cases, so 0.3, 0.4, that's why we have 0.7 right here. Okay, therefore, if you now need probability that x is equal to 1, given that probably y is equal to 2. So that will be equals probability that x is equal to 1 and y is equal to 2, the joint probability, all over the marginal probability of y being equal to 2, which is 0.7. That gives you 0.4286. So conditional density for continuous now follows the same kind of idea. So for continuous random variables, now f of x given y such that for x given y is equal to f of x comma y all over f of f sub y of y, like that. So then we talk about the idea of independence. So the two random variables are independent if knowing one variable gives no information about the other. Then you say they are independent. So independence, for the definition of independence now, random variables x and y are independent if f of x equals x comma y equals y is equal to probability that x is equal to x multiplied by y is equal to y. So in that case, now the two variables are not dependent for all x and y in that case. So the continuous case, for continuous variables, you have that f of x comma y is equal to f of x of x of x multiplied by f sub y of y. So an example with when we talk about independence of dice now. So for two fair dice, probability that x is equal to 3, y is equal to 5 is equal to 1 over 36. So in this case, so in this case, that is because probability that x is equal to 3 is 1 over 36. Probability that y is equal to 5 is 1 over, sorry, probability that x is 3 is 1 over 6. Probability that y is equal to 5 is 1 over 6 also. So see the marginal probabilities, probability that x is 3 is 1 over 6. Probability that y is 5 is 1 over 6 because they don't have anything in common. So the product now will be probability that x equals 3 multiplied by probability that y equals 5. That's 1 over 6 times 1 over 6. And that is 1 over 36. And that is why the other time when we said that for two dice, right, any combination of x and y you have will always give you 1 over 36 because they are independent. You have 1 over 6 times 1 over 6 in each case, and that's 1 over 36. Therefore, the variables are independent in that sense. And of course, this is another way to just simulate the same situation right here. In summary, we see that in summary, we have this that joint distributions describe probabilities involving multiple random variables simultaneously. And we have important concepts which include joint probability mass function, which is P of x equals x, y equals y, marginal distribution, P sub x of x is summation over y of P of x comma y. And we have conditional probability, which tells us that probability that x equals x, given that y is equal to y, is the joint probability that x is x and y is y, all over probability that y is y. That's the marginal probability in that case. So independence condition. So if two variables are independent, that one doesn't say anything about the other, like in the case of a die of two dice, right? So the joint probability of two independent variables is the product of their individual probabilities. So joint distributions are fundamental in statistics, machine learning, data science, and Bayesian inference. Of course, I already have a playlist on probability, very comprehensive playlist on probability. You want to check that out in case you want to get. So there, I took time to really explain, did a lot of examples and everything. So you just want to go to my channel and then check out the playlist. Just click on playlist like this, and then you can scroll down to where you find videos, the playlist on probability. Where is it now? It is way earlier. Um, Probability. Yeah, I have 17 videos on that. So there I have the whole introduction to probability all the way down to Python code for convergence, central limit theorem. We are still going to, so we've been seeing some of these things I've treated, we are seeing them again. So this joint probability distribution, now marginal distribution, extensively dealt with. So you want to check that out if you're interested in that. Okay, so I'll just flash the practice problems. So because all you just need to do is look at the examples and try them out. You have 1 to 2 here, and here you have 3 to 4. Okay, then you have 5 and 6. So if you need clarity, you can check the probability playlist. You have 7 and 8 here because this is more like a revision. And then you have 9 and 10, like that. You have 11 and 12. You have 13 and 14, 15 and 16, then 17 and 18, and lastly, um, 19 and 20. So try your hands on this as much as possible. Let me know how helpful this video is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, why not? Go ahead right away, hit the notification bell. Subscribe, hit the notification bell so you can always get alerted each time a new video is released. You can also become a member of this channel by clicking on join. That gives you special privileges like getting to see some videos first or being the only ones to see certain videos. You can also request for PDF copies of my notes with which I teach. We can hang out together to discuss whatever interests you on my channel. And ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.